Actually, you have already know what do you mean by simultaneous equation system and how you identify the system and what are the exact condition needed for solving the model. Today what I will do, I will basically give some example from the real life situation to let you know how the model works and how do you actually identify the parameters of the model and what are the necessary conditions so that you end up with a meaningful solution. Now, let me give some example of simultaneous equation model. In the usual regression model, y is the dependent variable and x1, x2 up to xk are the independent or the explanatory variable. Now, the crucial assumption is that x's are independent of the error term u of the model. However, sometimes these assumptions are violated. Explanatory variable of any equation can be dependent variable for the other equation. In reality, what we have is simultaneous equation structure where several variables are jointly determined, that is, the simultaneous equation system distinguishes between the predetermined versus jointly determined variable, exogenous versus endogenous variable. Now, simple possible example is the demand supply model. Suppose we write the demand function as demand as a function of price only along with the disturbance term u, where dPu are the quantity demanded, price and the disturbance term denoting the random shift in the demand function respectively. Similarly, supply is a function of price and also the error term. Now, we assume equilibrium to holds. So, Q is the equilibrium value of quantity implying demand is equal to supply. Now, equating demand with supply, we can determine the equilibrium value of quantity and price. Now, since both quantity and price are jointly determined variable, changes in error term of the demand equation is likely to change the equilibrium value of prices. Thus, the covariance between price and the error term of the demand equation is not 0. Thus, the estimation of the equation by ordinary least square produces inconsistent estimates of these parameters. Consider another example of simultaneous equation system. This is a simple version of Keynesian income determination of the model. Consumption is a function of income. So, you assume linear function, beta naught is the intercept, beta 1 is the coefficient corresponding to income and the error term, and in equilibrium yt equal to consumption plus investment, where investment is exogenous to the model. Now, the coefficient of the income variable in the consumption equation is known as marginal propensity to consume, and you assume coefficient of marginal propensity to consume is less than 1. That is, you assume the coefficient lies between 0 and 1. Now, since investment is exogenous, it is not correlated with the disturbance term of the model, that is, covariance between investment and the error term is 0. Here also you find that changes in error term of the consumption function will change the optimum solution of income, which is the explanatory variable for the consumption function. Hence, the covariance between the explanatory variable y and the error term u is not 0. Thus, Here also OLS cannot be applied, and application of OLS to the consumption function result in biased and inconsistent estimate of the structural parameters. You can treat this as a simultaneity bias. So, what the result we are getting? That application of OLS to the simultaneous equation model will lead to biased and inconsistent estimate of the structural parameter, which is known as simultaneity bias. So, if you determine the OLS coefficient, you can find they can show that, no? So that you can find the OLS quantity. Now, if you take probability limit of that OLS estimator, you can find that estimator will not be equal to the true parameters of the model, and hence you are getting the inconsistent estimate of the structural parameters. And such inconsistency will arise even if you extend your sample size to infinity. That is, such kind of inconsistency is not only due to the small sample bias. Now, you have seen that in the structural equation you cannot find the OLS estimate of the structural parameters. So, this is because there exists problem of collinearity between simultaneity between the error term and the explanatory variable of the model. Now, from the structural equation model, you can eliminate the explanatory variable of the equation and can express the equation only as a function of predetermined or exogenous variable. For example, in the present case, you can write consumption as a function of investment only, which is exogenous to the system. Similarly, income as a function of only exogenous variable. Such kind of representation of the system is known as reduced form of the model. So, in the reduced form of the model, what we get? We explain the dependent variable of the model only as a function of exogenous variable or the predetermined variable, and hence in the reduced form of the model you can apply OLS estimate. Now, but our purpose is to estimate not the reduced form of the model, rather we want to estimate the structural form of the model. So, given the estimated value of the reduced form coefficient, we can try to find out the structural form of the model, the structural parameters of the model. Take another example. Quantity demanded is a function of price and income, and similarly quantity supplied is a function of price and rainfall. In the present example, you are taking quantity as a linear function of price and income, and similarly quantity as a supplied as a linear function of price and rainfall. Here price and quantity are endogenous variable and income and rainfall are the exogenous variable. Now, as in our earlier case, using this notation, you can have the reduced form of the system where quantity is expressed only as a function of income and rainfall, and similarly price is expressed as a function of income and rainfall. Such kind of representation of the reduced form parameter, reduced form equation for the quantity and price expression are as follows. So, here you have quantity as a function of only income and rainfall, which are the exogenous variable, and similarly price is expressed as a function of income and rainfall, which are also the exogenous variable. Since quantity and price are expressed only as a function of exogenous variable or predetermined variable, in these two equations you can apply OLS and accordingly get reduced form parameters. So, reduced form equation is known as, the reduced form equation are given by quantity as a function of pi 1 plus pi 2y plus pi 3r plus v1, p plus pi 4 plus pi 3y plus pi 6r plus v2, where v2 and v1 and v2 are the error terms and pi 1 and pi 2 are as follows. These are the reduced form coefficient. Now, using the estimated value of reduced form coefficient, you can generate the original structural form parameters, which is our basic interest, because our basic interest is to find out the reduced form not the reduced form parameter, but the original structural form parameters A1, A2, B1, B2, C1 and C2. So, in this case, we can successfully estimate the structural form parameters given the reduced form parameters. This method of finding out the structural form parameters from the reduced form parameters is known in the literature as method of indirect least square. It is called indirect least square because we do not apply least square to the original structural equation. The indirect least square method, however, does not always work. So, we will first discuss the condition under which it works, and to discuss this issue, we first have to clarify the concept of identification. So, let me start what do mean by problem of identification. The concept of identification is related to the consistent estimate of the structural parameters. So, let me ask the following question. Given the estimated value of reduced form parameter, can we get back the structural form parameter? Now, if the answer is yes, then we say that the parameters are identified, and if we have unique solution, then the parameters are just identified, and if you have multiple solution, then you have the case of over identification. If the parameters, if you do not have any solution, then the parameters are not identified, and in this case we say that the parameters are under identified. So, it is not always possible to get back the structural parameters from the estimated value of the reduced form parameters. So, let me have some general expression. Let G is the number of equation of the endogenous variable, K is the number of exogenous variable or predetermined variable, and there are G number of endogenous variable denoted as Yt. Yt is the notation for the endogenous variable, and Zt is the notation for the predetermined variable, and gamma is the coefficient matrix, and similarly beta, capital B is the coefficient matrix, and this, from that you can have structural equation. The notation are as follows, and accordingly from the structural form parameters you can generate the reduced form parameters, where each of the dependent variable are expressed only as a function of the predetermined or exogenous variable. Now, what we find, if we estimate the reduced form equation, we get Gk number of parameters, but you have to determine Gk plus G into G minus 1 number of total number of variables. So, you need another G into G minus 1 restriction. So, that basically implies, since you have to solve for more number of parameters as compared to unknown, because if we apply reduced form estimate, the pi's can be said to be known quantity. You know the value, you know the numerical estimate of the pi parameters. So, given the estimated value of pi, it is not always possible to determine the endogenous variable or the endogenous parameters of the model. Now, problem of identification arises because of observationally equivalent structure. Now, the two structure is said to be observationally equivalent if both the structure have same reduced form. That is, if you have observationally equivalent structure, then same set of data may be explained by more than one possible way, and this implies we may construct more than one possible hypothesis, each of which will account for the observance of fact. So, that basically implies without absence of any a priori restriction, it is not possible to determine all the structural parameters of the model. Now, problem of identification arises because of observationally equivalent structure. Now, the two structure is said to be observationally equivalent if both the structure have same reduced form. That is, if you have observationally equivalent structure, then same set of data may be explained by more than one possible way, and this implies we may construct more than one possible hypothesis, each of which will account for the observance of fact. So, that basically implies without absence of any a priori restriction, it is not possible to determine all the structural parameters of the model. So, we have to identify the best possible hypothesis from the alternative hypothesis without a priori restriction. Example where demand is expressed only as a function of price and supply is expressed only as a function of price and equilibrium holds. Now, take linear expression of 1 and 2. If we take linear expression of 1 and 2, you get the equation 3, which is a linear combination of equation 1 and 2. So, if we multiply equation 1 by m and equation 2 by n and add them up, you get a linear combination of equation 1 and 2. Now, equation 3 is known as Mongrel equation, which have the same form as that of the original demand or supply equation. So, if we regress Q on P, we do not know with certainty whether you are estimating either demand equation or supply equation or the Mongrel equation. Hence, neither equation is identified. Now, since m and n are arbitrary, infinite number of such transformation is possible, and this proves the existence of observationally equivalent structure. That is, with the same set of data on Q and P, you can construct an infinite number of possible hypotheses, because you are not putting any restriction on the value of either m or n, and hence you have n infinite number of such linear transformation. That basically implies in order to identify the model, you have to introduce restriction into the model. Now, question, what kind of restriction do we need? The restriction can be either on the structural parameters or on the variance covariance matrix of the error term. Now, restriction on the structural parameter can be of two types. First of all, you can have exclusion restriction, or you can have linear or nonlinear restriction, that is general homogeneous linear restriction. That is, say for example, you use beta 1 2 plus beta 2 2 equal to 0, that is you are taking linear combination of the coefficient matrix. Similarly, you can have restriction on the variance covariance matrix of the error term. That is, you can assume the error term of one equation is not correlated with the error term of the other equation, and hence you get a diagonal sigma matrix, that is diagonal variance covariance matrix. That is, off diagonal term showing the correlation of the error term of one equation with the other is 0. Now, let me start with exclusion restriction. What do you mean by exclusion restriction? In exclusion restriction, what we do, we introduce some additional variable into the model and exclude it from some equation In this case, we are introducing rainfall into the picture and we are adding rainfall into the supply function and excluding it from the demand equation. Hence, the coefficient of rainfall of the demand equation is 0. That is why it is called exclusion restriction. Now, if we take the reduced form of the model, you get 4 reduced form coefficient. One is the intercept term, other is the coefficient corresponding to the rainfall equation, and this is true both for demand equation as well as supply equation. So, that basically implies altogether you are getting 4 reduced form parameters. But what is the number of parameters you have to determine? You have to determine 5 number of structural parameters showing A, B, alpha, beta and gamma corresponding to the demand equation and supply equation. Now, here demand function is identified, but supply function is not. What is the intuition behind it? If we take the Mongrel equation, taking linear combination of both demand equation and supply equation, you get quantity is expressed as a function of price and rainfall. Thus, the Mongrel equation can easily be confused with the original supply equation, but not with the demand equation. So, if we regress Q on P and RT, you do not know with certainty whether you are estimating the supply equation or the Mongrel equation, hence the supply function is not identified. But you can determine the parameters of the demand function because demand function is not confused with the Mongrel equation and hence it has unique statistical form. So, what is the gist of this result of the exclusion restriction? In order to identify the parameters of the equation, introduce some additional variable into the model and incorporate it in some of the equation and exclude it from the other equation. The equation in which we are excluding the parameters, that equation will be identified, and the equation in which we are excluding it, we are including it, that equation will not be identified. In the present example, we are excluding the additional variable rainfall into the supply function, hence the supply function is not identified and we are excluding it from the demand. So, in this part we have discussed some economic example of simultaneous equation system, and we have seen that if you apply ordinary least square to this simultaneous equation system, you get biased and inconsistent estimate of the structural parameter. The reason behind that, the explanatory variable of the model are correlated with the error term, and the basic assumption that the explanatory variable of the equation must not be correlated with the error term of the OLS regression is violated, and as a result you are getting biased and inconsistent estimate of the structural parameter. We have seen how we can use the reduced form equation to get the structural parameters of the model, and this problem of getting the reduced form getting structural parameter from the reduced form equation is known as problem of indirect least square, and this method is known as indirect least square because you are not directly applying OLS to the structural equation, rather you are using reduced form equation, apply OLS to the equation, and then you get the empirical values of the structural form parameters. We have also discussed how we can identify the parameters of the simultaneous equation model, because the parameters of the simultaneous equation model cannot always be solved, and we need some restriction into the model. Actually, you have to introduce some restriction in order to get the values of the parameter. We have also seen that restriction can be either on the structural parameters of the model or can be variance covariance matrix of the error term. Now, coming to the restriction of the structural parameter, you can see that there are exclusion restriction, that is you are excluding some of the variable from some of the equation and including it to the other. The variable which are excluded from some of the equation takes the 0 value, the corresponding parameters takes a 0 value, and as a result we say that the parameters are excluded from the equation. On the other hand, you can have the restriction on the variance covariance matrix of the error term, and we have also discussed how we can use the variance covariance restriction in order to solve the model. In the next class, what we will see how we actually identify the parameters of the model, and in order that we need some restriction, and what are the actual restriction to the model.